Welcome back. Today, I'll discuss the second part of this important topic of electric field as potential gradient and a few numericals and few other theoretical problems based on that. Let's see what we have done till now. We have proven that electric field is minus dV by dr. Normally, if one-dimensional electric field is given, you can very well change it as dV by dx or dy or dz. If the electric field is in multiple directions, then it will change something like this as minus curly v by curly x along x-axis, curly v by curly y along j-axis, and curly v by curly z along k-axis. This has been assumed that r is a function of only Cartesian coordinates as x, y, and z. R is a function of x, y, and z, and they are not interdependent on each other. In that case, this dV by dr can be changed into rather we can say the whole variation of v with respect to r can be split up into three parts: the variation in v with respect to x, variation in v with respect to y, variation in v with respect to z. There are very good and important numericals based on that. We'll do that later on. And the same thing can also be written in another way as v is equal to minus EdR. Again, I'm taking a simpler case. I can change it as EdX. I'm assuming the field and the field is acting along only one axis, that is x-axis, or it may be acting only along y-axis or only along z-axis. In that case, you don't have to take multiple cases. So this is the simplest part, simplest case. Let's discuss a few numericals based on it. How the questions can be given, and we also will also go to the electric field generated by charged sphere and a charged spherical shell. Those cases will also be discussed in this lecture. Let's start with a very simple case that you have been given some value of v. V is 3x square plus 4. The units of v are either volts, or you may also write them down as joule per coulombs. And the question says find out the electric field. So the electric field would be something is equal to minus dV by dx in this case. So negative sign and differentiation of the above equation, which turns out to be 6x. After differentiation, we have got electric field whose units would be Newton per coulomb or volt per meter as well. Volt per meter. You can also write it down. So now E is equal to minus 6x. And it is important over here that I was assuming it to be dependent only along x-axis. So E is equal to minus 6x. You can very well write it down as minus 6x I cap. There was no y or z components, so correspondingly 0 j cap and 0 k cap. So what do you get? What information do you get from this thing? Electric field is equal to minus 6 times x. So is this electric field a constant electric field? The answer is no. This electric field will go on increasing along x-axis. So at x is equal to 1, 2, 3 and 4, as x increases, this if I put x is equal to 1 meter, its value would be 6 Newton per coulomb. At x equal to 2 meters, its value will be minus 12 Newton per coulomb, and so on. And since there is a negative sign, they are showing that they are pointing towards negative x-axis. So electric field is stronger as you go away from origin along x-axis, hence weaker near the origin. And x equal to 0, the electric field will be 0. And as you go to the other side, again, as you will put x equal to minus 1, the electric field will become positive. That means at x equal to 1 meter, it will be pointing towards this direction. So just by knowing the expression for potential, a lot of information about the field can be extracted out of it. about the magnitude of field, about its uniformity or non-uniformity, about its directions, etc. Let's do one more question. What if potential is something like this? X square y z plus y x square z this is and something you may write it down. It's, let's say, x y z square, and then you have got y z x square, y square z x. Now this is the expression for potential. Clearly, the potential is not a function of x only, it is a function of x, y and z, all the three coordinates. And the units are, let's say, SI units are as Joule per coulomb. Now what would be electric field? Electric field is negative gradient of potential. The gradient of a scalar quantity becomes a vector quantity. You should keep it in mind. So electric field, now E can be written as minus, that I take as common, curly, this whole thing, curly V by curly X along I cap, this curly V by curly Y J cap, and curly V by curly Z K cap. Now what is this curly by curly X? Curly by curly X stands for partial differentiation. Partial differentiation means that when I am differentiating with respect to X, I'll assume Y and Z to be constant. When I am differentiating with respect to Y, I'll assume X and Z to be constant. And when I'll be differentiating with respect to Z, I'll assume X and Y to be constant. This is termed as partial differentiation, and it's denoted as, instead of d by dx, we write it down as curly by curly x. However, when there is only one parameter, then d by dx or curly by curly x become same. So let's proceed with this. What would be electric field? You differentiate this whole thing with respect to, first of all, with respect to x. So it becomes 2x y z, and this becomes 2, this becomes yz square, and that becomes again y square z I cap, plus you have got now curly v by curly y. Differentiate with respect to y, assume x and z to be constant, so it becomes x square z plus xz square plus 2y zx j cap, plus, now I differentiate the same equation, but this time I'll differentiate it with respect to z, and I'll assume x and y to be constant. So let's assume x and y to be constant, so it becomes x square y plus xy with respect to, so this becomes 2z plus, then this becomes again y square x k cap. Now this is the final expression for electric field. I may ask you, what is the value of electric field at the point 1, 2, 3? So just put in the value of x as 1, y as 2 and z as 3, you will get the value of electric field. And then the magnitude of electric field can be obtained as the square of the coefficient of I cap plus the square of coefficient of y j cap and plus coefficient of k cap square and whole under the root. That would be the magnitude of electric field. This is how you proceed to find out electric field when electric potential is given to you. The other way around is also possible. That is, you have been given electric field and you wish to find out the electric potential. So let's see how to proceed with that. Let's see. It's given that electric field at a place is 6x square. I'm assuming that it's acting only along x-axis, so I'm not writing down I cap. I've taken its magnitude. The units are, let's say, Newton per coulomb. you could have written it volt per meter as well. Now, how would you find out electric field? You know that E is equal to minus dV by dx. So V is equal to integration of E dx, negative of integration of E dx. Just put in the value of E, which is given to you 6x squared dx, and integration will turn out to be 6x cubed divided by 3, which is minus 2x cubed, plus some constant. That constant can be obtained from some initial condition. For example, the question may say find out electric potential where electric field is given that potential is 3 volt at origin. Then how would you proceed? You would say, okay, now let's put in the condition. It is given that voltage is 3 volts at origin. So I put x as 0 plus c. So I'll get the value of c as 3. Now put that value of c in the original expression again, and what you get, v is equal to minus 2x cubed plus 3. That is the expression for electric potential. And then the question may further say, and then find out potential at x equal to 2, x equal to 3, x equal to 1, whatever. You can just simply put in the value of that coordinate which is given to you. Let's do one more question. Let us say that it is given that electric field acting along positive x-axis is 2x cubed plus 4, 2x cubed plus 4 volts, Newton per coulomb. Given that V is equal to 10 volts at x equal to 1, find electric potential at x equal to 2, x equal to 2 meters. Now this is a complete question. So proceed as we did in the last part. How do you do? V is equal to minus E dx. So integration of E was 2x cubed plus 4 dx. The integration becomes minus 2 x4 by 4 plus minus 4x plus c. A little simplification. V is equal to x4 by 2 minus 4x plus c. After doing this, what you would do, you would put in the condition given to you. The condition is V was 10 volts at x equal to 1 meter. So I put x as 1 raised to the power 4 divided by 2 minus 4 plus c. So what do I get? 10 plus 1 by 2 plus 4 is equal to c. So it is 14 and a half, 14.5. So c is 14.5 volts. Put in this value of c in this expression, and what do you get? The expression for V, the complete expression for V, that becomes minus x4 by 2 minus 4x, and then the value of c, which is plus 14.5 volts. This is the expression for electric potential. Now the second part of the question says find potential at x equal to 2. So how will you do? You just put in the value of x equal to 2. Now in this expression, V is equal to 2 raised to the power 4 is 16. So 16 by 2, it is minus 8. And then you have got put x equal to 2, that becomes minus 8 plus 14.5. It was 16 by 2, okay. Minus 16 and plus 14, it is minus 1.5 volts. That is how you find out electric potential if field is given and vice versa. Let's do some more questions. They are actually, you may say they are part of the article itself. You have done Gauss theorem, and using Gauss theorem you obtain electric potential due to a charged sphere. While solving for, let's say this is a conducting sphere, or you may consider it a hollow shell. In both the cases, the charge will reside only at its outer surface, And inside, we have obtained during the lectures on applications of Gauss theorem, we obtained that electric field inside it is 0. And outside, at some point outside, it behaves as if the whole charge is concentrated at the center, and the expression for 1 by 4 pi epsilon naught q by r square. And a graphical representation was something like this. This was electric field versus the distance, you may call it x, you may call it r. Now, the electric field is proportional to 1 by r square. I want to draw a similar curve between electric potential and distance from the center of the sphere rather than just the electric field. How would you get it? You can pause the video here, try to solve it out and come back. I hope you have tried. Let's do what we can do with this. Inside the this hollow spherical shell or conducting sphere, electric field is 0. So what would be electric potential corresponding to that? We know that electric potential is minus E dx or dr. Since E is equal to 0, the integration of 0 is constant. So electric field inside the charged spherical shell was 0. That implies that electric potential inside that charged spherical shell is constant. This is interesting physically as well. Think of it that electric field is basically telling me how the electric potential is varying. And if potential is not varying at all, what would be electric field? If this point and this point both are at 1 volt, what is the field in this region? The field would be 0. As I go from here to here, there is no variation in potential. I am assuming that everywhere the potential is 1 volt. So what is the electric field? There is no electric field. Electric field will always be there only when potential is changing. And the field will be pointing in the direction of decreasing potential. If there is no variation in potential, that will simply imply that there is no electric field. So, in this expression, what do we get? Up till the point where we reach the surface, up till this point, the electric potential would be constant. It will be constant. And what about after that? 1 by r square? It is falling off as 1 by r square. So, I can now put in this value over here. It will be minus 1 by 4 pi epsilon naught q by r square dr. I can take out the constant things, 1 by 4 pi epsilon naught, integration of r raised to power minus 2 dr, that is equal to minus q by 4 pi epsilon naught, r raised to power minus 1 by minus 1, the negative sign gets cancelled out. And what do I get? Electric potential is 1 by 4 pi epsilon naught q by r. Outside the sphere, as we did earlier, it seems as if the potential is due to a point charge located at the center of the sphere, a spherical shell or conducting sphere. So it is varying as 1 by r. So it will be something like this. You can see the variation. The slope of the curve in this case would be steeper than the slope of the curve in this case. That means this is varying rapidly. If you double the distance, the field will become 1/2. But if you double the distance, the potential will become, if you double the distance, the field will become 1/4. Whereas in this case, if you double the distance, the field will become just 1/2. So potential is proportional to 1 by r. This is the expression and corresponding variation of electric potential inside a spherical shell. Now this leads us to very, very interesting questions. Let's see. I've got a charged spherical shell. It has got charge of 10 coulombs. Find potential. Let's say its radius is whatever, 2 meters. find out potential at a point which is located 3 meters away from it, which is located 1 meter away from it, and let's say which is located at 2 meters away from it. I wish to find out potential at a point which is outside the sphere, that is 3 meters away from the center. I wish to find out electric potential at a point which is lying on the surface of the spherical shell, that is at 2 meters from the center, and I also wish to find out electric potential at a point, let's say, inside the spherical shell, which is at a distance of 1 meter. Now, first of all, for this point, it is easy because it will behave as if, as I am outside the spherical shell, it will behave as if whole of the charge is concentrated at the center. So, what would be the expression? V would be 1 by 4 pi epsilon naught q by r. So, this is 9 to 10 raised to the power 9, 10 coulomb divided by 3 meters. This is the answer. This is the answer, no problems with that. Okay, leave it. Then tell me, what is the potential at the surface? No issues at all. Again, V is equal to 1 by 4 pi epsilon naught q by r. This is 9 to 10 raised to the power 9. Q is 10 coulombs divided by 2. Still the same. This is just, it was r has been replaced from 3 meters by 2 meters. So this will become, it is 45 into 10 raised to the power 9 volts. This is the potential at the surface. Now what is the potential at this point? Or at 1 by 2 meters as well. You can see from the expression, as soon as I enter inside the spherical shell, at all points potential is same, and it is same as that is at its surface. So this potential is the potential at the surface. So at this point, potential is still same, 45 into 10 raised to the power 9. What about this point? It is 45 into 10 raised to the power 9, and so on. So every point inside the spherical shell, any arbitrary point will have the same potential, that is 45 into 10 raised to the power 9 volts. This further leads us to interesting MCQs. Look at this question. Find out, this is, let's say, 10 coulomb charge given to a spherical shell of radius 3 meters, and it is given to us that a charge of let's say 2 coulombs is taken from this point A and is taken to point B. What is the work done? The answer is 0, because at all points on the surface potential is same. So work done is basically charge into initial minus final potential. So in this case, since VA and VB are same, work done is 0. What about this? Instead of this, let's say the charge is taken from point A, from here, to point B over here, which were 2 meters away from each other. I need not to tell you, work done is still 0. Because every point, not only on surface, every point inside this spherical shell has got same potential. And if they have got same potential, this bracket would always be 0, so work done is 0. Okay? Let's say from point A, the charge is taken to 4 different points. Point B, point C, point D, point E, like this. In which case, the work done would be more. Is W1 is greater than W2 is greater than W3 is greater than W4, or something like that. Some useless options would be given. We know in every case, no matter where you select the positions of A, B, C and D points, as long as you remain on the surface or within the spherical shell, work done is going to be 0. So this is very important category of numericals. Now let's proceed with the second example of Gauss theorem which we did, that instead of a spherical shell, if it's a charged sphere, what would be the shape of electric potential curve for that? Let's do that. This time it is a solid sphere made up of dielectric material, not a conducting sphere. A conducting sphere will behave like a that will behave like a hollow shell. This is a dielectric sphere. That means charge resides inside it as well. Outside it, the electric field is same. That is 1 by 4 pi epsilon naught q by r square. That is, it seems as if pole of the charge is concentrated at the center. That means correspondingly, if you integrate it, the expression for potential will remain the same as we did in the case of spherical shell. At the surface, it will be q by r. But what about inside? Inside, the electric field is given as 1 by 4 pi epsilon naught. If you remember it correctly, it was qr by r cube, where capital R is the radius of this sphere and small r is the distance of point of observation from the center of point of observation, and it is inside the sphere. That means small r is less than capital R. How would you integrate it now? Just integrate it to find out potential. Minus q by 4 pi epsilon naught r cube, that's constant, and inside we have got r dr. This r will get integrated as minus q by 4 pi epsilon naught r cube r square by 2. V is proportional to minus r square, y proportional to minus x square, y proportional to minus x square. This is the case of a downward parabola. So the expression for electric field was something like this, proportional to 1 by r square. I told you outside the behavior would be identical as we did in case of spherical shell, holospherical shell. It will fall as 1 by r. However, in this case, inside, earlier the potential was constant, but in this case, it is not constant. Rather, I need a little more space. I draw it again. This time, the potential is a downward parabola in this case. So, this is the final expression. Outside, potential is proportional to 1 by r. Inside, potential is proportional to minus r square by 2. So, correspondingly, you can obtain the expression for potential at any point using this expression if it is given to be a charged dielectric sphere. I hope these are really, you will try a few more questions based on these. These are really very important categories, and this will lead us to another very important category of numericals on potential when we get concentric shells. For example, shell 1, 2, 3. First of all, we'll see some charges are given to these shells. First, we'll see what are potential at point this, and this. You need to know how to solve out potential for these points, and then there will be expressions for finding out the induced charges of one shell due to one shell on another shell. So these are a little tedious questions. We'll discuss that in the next part. I hope you will try in the meantime these questions. Thank you.